Okay, I think now the record is on. So, you know, I've been thinking like every year whether or not I should teach the influence line. And I think when we begin the new curriculum, or we don't have to, maybe sometime next academic year, I'll try to find a way to replace this with something more useful. But anyway, influence line is something that you have to know, because moving load is something that engineers have to deal with. Okay, the load that moves. And from the previous class, we have experienced the influence line of the determinate structure, right? And we know that we have the Muller-Breslau principle, that when we free the restraint of any design function, we want to know the deflected shape of the structure would resemble the shape of the influence line. For example, if I want to know the influence line of this reaction that's called RB, I can free this restraint. And when I free this restraint, it means that this load is free to move up and down, because that's a reaction resulting in your structure being able to move up freely like that. So this blue one becomes the influence line of reaction at B. Okay. Now Muller-Breslau gives you the qualitative influence line. That means it's just a shape, and it's qualitative, right? For quantitative, you need to use your structural analysis knowledge. Okay, for example, when you put the unit load right here, you know that the reaction is going to be equal to the unit load, and therefore this magnitude is 1. Okay, or when you have, let's say, the next one, so to try to complete this, if you want to know the shear, you need to free the shear so that the shear can move freely, right? And when the shear moves freely, that will result in your beam moving up in this part and then down in that part. So the influence line becomes something like this. Okay, influence line of the shear. And again, you know that when you apply the unit load, using your structural analysis knowledge, you know that this magnitude is 1. Okay, or the last one, the moment. Okay, you okay, let me try to just shear. Okay, just a quick review. And if it's moment, you free the moment by adding a hinge, right? And that means the your member will be able to move freely like that, and resulting in the shape, the form shape of the structure like that. Okay, and you will get the influence line of your moment generally look like that. Influence line of moment. Okay, and this size is going to be maybe the moment is a function of the unit load and location. Okay. Yeah, that's not very clear. Let's remove that. Okay. All right. So that's a basic idea. Now, from this, we know that we can use the Muller-Breslau idea. That is, if we try to free the restraint, we're going to have the deflected shape or deformed shape of the structure that will resemble the shape of the influence line. That would be a great help. Okay. I used to talk about the influence line of truss, but I don't think it's that useful anymore. So I'm just going to skip that and head to the influence line of the determinate structure right away. Okay. You guys ready? Let's hope so. Okay, from this idea that we free the restraint of the design function that we want to know the influence line, it means that we can actually deal with the same concept with the indeterminate structure as well. So let us take a look at this beam. I think for clarity, I have a note actually. I don't know if I can. Okay, have a note. So in fact, I can use this. Okay, so let's see if I have the indeterminate structure. Not the same. But now let's say it's like this. Okay. And I'm going to call this A, B, and C. Now, if I want to know the shape of the influence line of RA, I can do the same by, remove the restraint of RA. So when I remove the strain of RA and I will enable the reaction at A to move freely, what I'm going to have is something like this, right? Again, it used to be able to do that just yesterday, but now it's too much again. Okay, so it's fine. And her to draw again. So it's like I still have this, right? And then the reaction at A is so ready to move freely. So without restraint at A. RA is able to move freely now, correct? So what do you think is going to happen? It is going to push up this beam, right? So we're going to have the deflection here at A, but unlike the case that we used to have in the determinate structure, when you remove the restraint in the determinate structure, it means that your structure is some sort of unstable and it can move freely, just like you have a hinge at the door. But now, because we have the indeterminate structure now, when I remove one restraint, what you have is a perfectly determinate one. So when RA is going to move freely up and down like this, it means that your structure will now deform just like the deflection of a simple beam. Can you see that? It's like forget about the calculation or anything. Just think about a simple beam now, and you are going to apply the load because we remove the restraint at RA, right? So RA becomes just the external load. So this is what is going to happen. Okay, so we now know this say Muller-Breslau gives you shape or qualitative. Now quantitatively, you know that this is the unit load. So what you know that is that this is going to be equal to 1. Right? So similarly, say if I do the same with RB, now what am I going to do? I am going to remove the restraint at B, right? So I now have a reaction B pointing upward like that, and the beam is going to move freely up. And the deflected shape is now going to be like this. Okay? So again, that Muller-Breslau gives you the shape, and your structural analysis knowledge will tell you that this is going to be 1. And similarly, for C, it's going to be pretty much like what you see with RA, right? Remember, it is the major difference is that you no longer have a straight line. Okay, so now I think the shape is fine. The problem is, what if we want to know the ordinates, the height of this influence line at more points than just where the reaction is itself. We know that this is going to be 1 here, 1, 1, 1. What about the rest? We need to find a way, the proper way to say, give you the easier way to obtain that. Okay, so let's say here, I'm going back here with this. Yes. Beam A, B, and C. Okay. Now I want to know I want the influence line of RB. Okay. So I'm just going to remove B back to basic. Basically, what I want is the magnitude of RB when I place the unit load anywhere on this structure, correct? So RB, it's the magnitude of RB when, say, the unit load is placed anywhere. That's not where, anywhere. Okay, so what I can do now is I'm going to look at this and use your beloved method called the force method, if you can recall. So I can apply the unit load here at any x direction, x distance. Okay, so that's one. Now, of course, when you have the load, you are going to have the deformation. Remember the force method. Okay, this is the deformation at B due to the unit load at X. Okay, so we can call that this delta Bx. So maybe with the extra note saying that deformation at B caused by load at X. So we call that delta Bx. Okay. So now let's move on. If I want the deformation, the RB itself, I can also apply the unit load at B, right? So say apply at B. So when I apply the unit load at B, this is, if this is called the previous one, this is the deformation at B due to the unit load at X. When I apply the unit load at B, I will have the delta BB, correct? And this is going to be the deformation when the unit load is here, which in turn, if I multiply this by RB, the deformation caused by RB is delta BB RB, correct? If the deformation caused by unit is delta BB, the deformation caused by RB is delta BB multiplied by RB itself. Now back here, oh, I'm running out of space very quickly. Need more. Okay, so from here, remember, I want to know the reaction. I want to know the reaction when I place the unit load at X. Okay, so the reaction is related to the unit load when you apply it here. So in the end, I can write this equation. Delta Bx, which is the deformation here at B, plus deformation at B caused by that reaction, right? So it's delta BB RB equal to 0. So this is the whole form of the force method. So from this, I can say that RB is equal to minus delta Bx divided by delta BB. Sorry, delta looks like an 8. Okay, now let's say that's just one X. If I want more, I have to move the unit load to the new location, but I can still call Rx, right? And this process will be repeated until I get as many ordinates as I want. Another thing is that, do we have to move the load and calculate this all the time? Luckily, no, because let's go back to the handout. Okay. Have I stated here? Okay, so here we are. I have shown you that in the end, RB is equal to, oh, sorry, here, not that one. My apologies, is this one. But like I say here, doesn't mean we have to put the unit load in various locations to calculate delta Bx. No, there is one theory called Maxwell's theorem of reciprocal deflection, meaning, go back to the note here. Delta Bx see if we can write this. Okay, let's say you want this. And this is unit load at X distance. This is called delta Bx, right? Deflection at B caused by the unit load at X. But Maxwell reciprocal theorem says that this is equal to delta XB. So what is delta XB? Delta XB is the deflection at X caused by unit load at B instead, right? So that is delta XB. Now it means that you can place the unit load at the location of the reaction and calculate deflection at any point X instead. So instead of placing the unit load every time, you place the unit load once and calculate displacement at various locations instead. So basically that's it. And once you can use that to replace it here. So from RB equals delta minus delta Bx over delta BB. This is also equal to minus delta XB over delta BB by Maxwell reciprocal theorem. Okay, they are equal. Unbelievable, but it's true. And this is the main reason why our stiffness matrix should always be symmetric because of this. Okay, say now it means that you need to calculate deflection by using the force method, and once you have the deflection, you will be able to obtain the reaction at B. Okay, and once you have the influence line of one reaction, it means that your structure is now turned into a perfectly determinate structure with one known reaction. So the rest should follow. But that's basically everything for the indeterminate structure. So the most important thing, the bottom line, is to obtain these. Deformation. Obtain deformation. And you shall get your one influence line of the reaction. And when you have the influence line of the one reaction, you have a determinate structure, and the rest will fall into place. Okay, so any question? Please, any question?
It can be said that delta Bx and delta Xb is the same, right? Because
they are equal. They are not the same, but they are equal. Okay, just select the right vocabulary.
Okay.
Mm-hmm. It's the deflection at okay. Delta Bx is the deflection at B caused by load at X, which by Maxwell reciprocal theorem happens to be equal to delta XB, which is deflection at X caused by unit load at B. So you cannot say they're the same. You should say they are similar. Well, actually similar is the same, right? But they are equal, okay? They're not the same, they're not similar, but they are equal. So we are talking about this deflection is equal to that. All right. So maybe it's better to look at the example, maybe. So let's say I'm going to give you this. You guys have this already? Oh, maybe not. Have I given you this?
Not yet. Not yet.
Not yet, really? So sorry, my bad. Wow, I was confused about something. So I have to go to Facebook and paste and post it now. So could you please wait for a minute or two? Okay, my apologies. My very, very deepest apologies. Okay. Ah, geez. Okay, I think I'm in the group now. Crikey me, I think, okay, that's it. Nope. One moment, please. I think it's quicker for you to load from Facebook than from the Zoom. Okay, okay, it's on. Can you guys go to the our Facebook group and get it? And tell me when you have it. Okay.
Yeah, got it.
You got it?
Yes, yes.
I was gonna pause the video, so I guess I don't have to anymore. Okay, so let's say we are back in business. Okay, right. So can we look at this example now? Everyone's ready? Hello?
Yes.
Okay. All right. So let's say the key is we are going to try to construct the inference line for reactions VD and MD for this beam. The key is that once we can obtain the deflection, will be fine. Okay. We're going to use a 1.5 meter increment. So that means we're going to try to find the values for these points like that, every 1.5 meters. Okay. So generally, this is very important, and I hope every one of you who is here, just as 6 of you, will get this correctly. Okay. Generally, I don't have any intention to treat or to test, rather, to test how you can calculate the displacement. Okay, that was done long time ago, the calculation of the displacement. So generally, I intend to give the information about the displacement or deformation, rather by giving you the formula or something. So most of the time, students don't know how to use the formulas to calculate the displacement, which is really sad. Okay, so let's say for this case, the old school, if I didn't give you anything, you're going to have to try to find a way to calculate displacement. Okay, now, but first thing first, we have to turn this into some kind of a determinate structure. Okay, and I myself prefer the removal of RB. So let's say I'm going to get started by placing the unit load here. Okay, so you see my intention is to calculate the displacement of this structure, but instead of placing the unit load anywhere to try to get the deformation at B, now I place the unit load at B, and I will have, let's say, this guy is going to be delta 1B, correct? This, oops, not straight enough. This is going to be delta BB. This is delta 2B. This B should be not capital. Okay. Delta 2B, delta DB, and delta 3B. Okay, and since I don't intend to test you on how to calculate these values, okay, I rather give you the formula or the numbers. So in this case, let's say I am skipping this and give you the deformation right away. Okay, so let's say delta 1 is equal to 7.125 over EI. Delta B is 12 over EI. Delta is 12.94 over EI. You see, actually, this one is lower. This point is lower than where the load is itself, which is not surprising. And then we have delta D is equal to 10.5 over EI. And then delta 3 is 5.81 over ER. Okay. There's the sign convention here is a little bit tricky, because let's say we know that our influence sign is going to be upward. So if we say the upward is positive, these values given to you should be negative, right? Maybe. And now let's say we can use this information to obtain RB right away by simply using this formula. Okay. Now the ratio of this. Now the thing I hate about this is that, you know, when you divide this, let's say delta, oh sorry, RB, say when the unit load is at the 1, is going to be equal to, let's look at this formula. It's minus delta XB over delta BB. So the key is everything will be divided by the deformation at the reaction itself. You see that? And now the formula says negative, and you may think, okay, negative divided by negative, in the end I should get positive, and I have another negative here. So I don't know, I don't really like it very much, but let's say we all know that it's going to be positive, okay? So let's say if I want to have the value of reaction when the unit load is at this location, okay, at 1, simply it is this one, delta 1 divided by delta B, okay? So it's 7.125 over 12. Okay, and the sign is reversed. So then this gives you the value of, my handwriting is pretty blurred, so I'm gonna have to do this one more time to get the proper number. It's 0.594. Okay, so that is the value of RB when the unit load is at 1. So I can repeat this, RB when the unit load is at B. So you would expect, at least from the previous knowledge, that when the load is on top of the support itself, so it's 12 by 12. So that's one. Okay. We move on when it's at 2. So now you have 12.94 over 12. That is 1.08. We have 3 significant figures already. When it's at D, now we have 10.5 over 12. So that is 0.875. And then when it's at 0.3, becomes 5.81 over 12. That's 0.484. So these are the ordinates of your influence line. So it's pretty easy once you have the deformation ready for you. But the key is that when you are given this information, you must know how to use it. Okay, and I think the best way to try to explain the sign convention here that is negative is that you can look at just the deformation of the influence line, and the negative sign means that your reaction is going to give you, it's going to be the opposite direction of this. Okay, So now we have all the numbers. I can just use this to plot. I don't know. Yeah, let's try to. Oops, it's gone. You guys can just see the screen. It's gone now. So need to chat again. That's a bad omen. Plug-in required again. Okay, just 1 second. Okay, we're back in business. So now let's say point A, no point doing that, it's 0, right? Then we have at the 1, it's 0.984. Okay, at B, it's going to be 1. At point 2, it's 1.08. And then at D, it's 0.875. And then at 3, it's 0.484. And then 0 in the end. So basically, something like that. Okay, and here is 0.954. That the most important thing is that at 1 you're going to get 1, right? And then this is slightly bigger than 1. And it comes down to it is 0.875 is 0.484. So that is the influence line of RB. Is there any question? I wish I could superimpose this picture with the beam, but you know. So let's say you can maybe try to write the beam down here so that you feel what's going on. Okay, that's A, that's B, and then that's another support. Okay, C, right? Okay. So that is, remember the feeling. This is the magnitude of your reaction at B when you move the load around. Okay, is there any question? Hello? Now it means that generally, if I draw this beam again, let's say that's my A, that's my C. Now my RB is no longer unknown. Okay, so I can use this free body diagram to solve for my RA now, right? Can I do that? Okay, so now I can use sigma MC equal to 0. Okay, and what's going to be my RA? So I have RA multiplied by 9 plus RB multiplied by 6 equal to, is that it? No, remember you have this unit load always lurking, okay? And if you take sigma MC equal to 0, this distance is x, right? So this is going to be 9 minus x. So that is going to be equal to the unit load itself multiplied by 9 minus x. Okay, so with that, you can actually obtain your RA. Okay, so let's say I'm going to try to finish this first. You can shuffle this a little bit. That RA is going to be equal to 1/9 multiplied by this guy, 9 minus x. I'm just leaving one out because that's kind of absurd. But I use green to let you know that this is from the external unit load minus RB multiplied by 6. Okay, so now RB is from this information, right? Now you have RB. Okay. Meaning you can just say, I'm trying to make the compact. RA, when the unit load is at 1. Now it means that you use RB. I don't need to be so stingy with the area. Okay. Now you should know, you can do this yourself. You don't have to. I never did this, but since I think I got a lot of time on my side, I should try to demonstrate things very, very clearly. So B is 0.594 and your X is now 1.5, correct? You just use these values and plug in this equation. We try to, okay, yeah. Now plug this in this RA equation. Okay. Now you should get the value. And let me try it again for clarity. X is so that's 7.5 now, right? Minus 0.594. Oh no, I can't do this. It's a silly calculator. The 0.594 multiplied by 6. Yeah. Okay. Plus 7.5. That's divided by 9. Right? What? I got a strange number. Can you help me check this? Somehow this didn't feel right. It's 0.594 by 6. Two times got the two different values, but I think this looks closer to what I have on the node. Okay, you get this number, maybe. Hello. And the next one, when the unit load is at B, RB is 1, X is 3. Okay, so that's a minus 6 and then 6, so that's 0. So it makes sense to get RB equal to RA equal to 0 here, right? Otherwise, I mean, it's wrong. And when we move on to point number 2, RA is 1.08. X bar becomes 4.5. Okay. So, you know, it's not surprising to know that RA is going to become negative, right? Because think about it. In your structure, it's like this. And now you have the load here. This one is just going to go up, right? the portion of the beam here wants to go up. So your RA should now become negative, right? Simple, say, seesaw effect. And since nobody's helping me out, let me give you the number right away, okay? Because this is now repetitive. So that is about minus 0.303. And you can repeat this when it's at D, that's 0.875, right? And when it's at 0.3, this is 484, this is 6, this is 7.5. Okay, you can do the calculation by yourself. Just once you get the idea, which is about 213, and this is 113, and look like 3. You can 213. Okay, and once you plot this, you're gonna get something like this. Okay, it has to be 1 here, right? And then it has to be 0 at B, and you know, whatever the numbers you have, it should reflect the curve. Okay, so here is, say, I use the solid line. Okay, so here at 1, that is the 0.437, that's 0. So that is minus 0.303, minus 0.213, and minus 0.113. So this is the inference line of A. Okay, is that any question? You see, it's just a game now, because once you have the deformation at any point, you must know how you can utilize this. And once you have this going, you know, you can solve one reaction, and the rest will just, you know, it's nothing. Okay. Is there any question? If not, I think we're gonna have a break. Okay, so let's fix this a little bit. This number is not correct. Okay, so it has to be minus 0.156. Is there any number wrong?
Add 2 and D as well. For D, I got negative 0.5.
They are all wrong.
Yes.
Okay. How much?
For D is negative 0.25.
0.25, really?
Oh, sorry, for D.
D, okay.
Yeah. I tried to calculate.
And at 2. What about 2? Is that correct?
Negative 0.22. Yeah.
Okay, let's I'm on it now. So let's say 6 point at plus 4.5. Yeah, right. Okay, so thanks for that. So that's gonna be minus 0.22 minus 0.25 and then minus 0.156. Okay, is there any more question? Thanks a lot for your help. Okay, so you can have a break now, I suppose.